Okay, so we're recording. I hope everybody had a good break. Welcome back. Hope it was nice and relaxing, and maybe you found us a little bit of time to keep your math skills polished. But anyway, welcome back either way. Here's a quick reminder of the last point that we made last time. We were talking about how to turn double integrals into iterated integrals, and notice that you can do the slicing in either order, or said differently, you can put the differentials in either order. How do you decide which way is better? Right? You can do either. Which one, though, is more desirable for you? It really depends. And rather than do it both ways every time, and then make the decision after the fact, I have certain guides, general approximate rules that very often will give you the best choice, but not always. And so these are just guides and no more. So the big idea is you want to avoid getting ugly functions in your bounds, in your inner bounds. Not because it's hard to plug in bounds, once you find the antiderivative. That's not the problem. The problem is that if you have something ugly there, then once you plug it in, once you evaluate that inside integral, that is your integrand for your outside integral. And so ugly functions on your inner bounds means you're going to have ugliness in your outer anti-differentiation challenge, whatever that's going to be. Okay, so how do we avoid that? Where did this come from? That square root of y came from the fact that I had to solve for x. Why did I have to solve for x? Well, because I put dx on the inside, right? And solving for x was bad here because x is the input variable, not the output variable, right? So the rough rule of thumb then is whatever is your input variable, and again, in this case, I feel like x would naturally be viewed as the input variable. Whatever your input variable is, put that on the outside. And then the thing that you'll have to solve for is the thing you've already solved for. Your integrand, you shouldn't have to invert any functions, and if you don't have to invert a function, then hopefully your bounds will be easier. So again, just a kind of a rule of thumb. More often than not, this is good advice, and it's a good streamlining process. Okay, everybody happy with that? Ring a bell. Everybody remember this last example we did? Okay, here's another. I'm going to call it another example. It's really kind of two examples, but again, the upshot is to learn a lesson and get some guidance on how to choose whether I should do dx dy or dy dx. Starting with our domain, it's this triangle here with certain corners given. We're only thinking about the process of turning a double integral into an iterated integral, so we're not going to worry about what the integrand is and where that came from, and does this represent mass or population or probability or what. Let's not worry about that part. We're also not going to worry about how to evaluate after the fact, other than we want to try to make it look as easy as it can be. We're going to just focus on this phase 2 only part of the problem. And the way I've got this set up here, y, so our outer bounds, y, you see, goes from 0 to 1. Right? No sweat on the outer bounds. We then fix a value of that outer variable y, and then we ask, well, what's the range of values of next our inside variable x? Well, our lower bound for x comes from that point, which is on that line, which has an easy equation. And so I can solve for x without too much trouble. X is just y. On the other hand, the upper bound for x comes from that point, which is on that curve, which again has a pretty easy equation, right? This curve right here, straight line, contains a couple of those points. By the way, thank you, picture. The picture tells us which 2 points define this line that defines the upper bound. You got to have a picture to be able to make good choices as to, wait a minute, which line do I pick, right? And solve for x, and x is 2 minus y. Okay, so that worked out great. Nothing ugly in the bounds. Very straightforward. By comparison, though, let's see what would happen if we made a different choice. What if we were to do x slicing on the outside? Actually, let me do this with a different color. X slicing on the outside. So x, it would seem, goes from 0 to 2. You'll notice that's not what I have written there. But let's ignore that point for the moment. Let's look now at a value of x. We'll fix a value of x. Let's think about the range of values of y. Y conveniently starts at 0. Right? Y equals 0 is always your lower bound. Looking at your slices here. Here are what your x slices look like. Right? Y always starts at 0. That part's looking good. Here's the bummer. The bummer is the upper bounds. The upper bound for y comes from that point, which is on that line. Oh, wait a minute. Is it? Because here's the thing. For this value of x over here, the upper bound point, it's on this line. So which is it? Is it this line or is it that line? Which line do I use to find the formula for the upper bound? And you can see, depending on what value x is, you get 2 different answers, depending on where you are in this process. And I'm going to say that's a problem. Right? This is bad. We can't have 2 formulas for our upper bound. Our upper bound needs to be a formula. So the way we fix this, and you can see in the way I have this written already, I have to break up the x range into 2 separate chunks. There's one story for these values of x. Right? For these values of x here, when x is between 0 and 1, my upper bound for y comes from that point, which is on that curve, which has easy equation y equals x. Solve for y and y equals x. But that's only for those values of x. I then separately have to consider values of x between 1 and 2. Right? For x between 1 and 2, my upper bound comes from that point, which is on that different curve with a different equation, in which, when I solve for y, I get 2 minus x. Right? So, sad story. We made this seemingly innocent choice about which way to slice, right? There was no clear which is the input variable, which is the output variable. There was no solving for x or y either way. Not going to be an issue, right? And yet, this first solution turned out great. The second one is double the effort, because I've got 2 separate integrals that have to be computed, and that's, well, call it double the effort. Not that either one is particularly worse than the original, but still, there's 2 of them. All right, does everybody see what happened there? Now, there's a lesson to be learned. There's a streamlined point of view that I have on this, and let's develop that idea. Where is the streamlining? What is it fundamentally that made me have to turn this into 2 separate integrals? And what it is that I had my upper bound determined by one curve for a little while, and then subsequently another curve. So the point that defines the upper bound was on the green curve, and then at some point it jumps over to the blue curve. Everybody with me? So now, how'd that happen? How did the point that defines the upper bound, it was on the green curve, now it's on the blue. How did it get from the green curve to the blue curve? Well, it jumped over at the intersection point. That was too many little dots. It jumped over where the curves intersect. And typically, when two curves intersect, they make a corner. So this is my sort of rule of thumb. Try not to slice through corners. So, in other words, you can kind of anticipate this happening. This, having two separate integrals at the very start when you say, alrighty, I'm going to do my X slicing. My X slices look like this. And boom, right there. I've sliced through a corner, hoping to be able to just continue along, right? It is the fact that I sliced through a corner that is what is the giveaway that this curve intersected that curve, and thus the two different equations. So, just as long as you don't slice through corners, you would expect good news. What do you think? Everybody happy? Okay, so now real quick, I will recognize that in this original approach, when we were slicing first perpendicular to the y-axis, technically my very first slice hits two corners. Here's the thing, slicing through a corner, what the slicing through a corner really means is that you expect to have to stop whatever integral you were developing and start a new integral. And the thing is, when I got to this value of y, I was not previously working on any integral. I was going to start a new integral here anyway, so no problem, right? And then slice, 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 and then the very last slice, I slice through a corner again. Again, no problem. I was done anyway. I don't need to start a new integral because I'm done. So that's fine. It's okay to slice through corners at the very beginning and at the very end. Just try not to slice through corners mid-process. Okay. All right. Is everybody happy with that? Okay. So you got two kind of, rough general rules that'll guide you in good ways. Think about what's the independent variable. Choose accordingly. Try not to slice through corners, again, if you have the choice. Okay. Here's another example. Sometimes the domain is not given. Well, it's not explicitly given. Sometimes the domain is something that you have to figure out as part of the solving of the problem as stated. So here we go. Suppose you have this paraboloid and this plane. And the question is to find the volume in between. So we've got this shaded region in here that I'm going to highlight in yellow, right? Which, just to make it easier to see, I'm going to draw it over here. There's the volume in between these two surfaces. Everybody good? Okay. It's not clear how this is an integral. Let's, very first step, think about what the Riemann sum approach to this is. I'm going to view this as being the amount of volume sitting above. Oh, let's see here. Choices. I will use orange here. Amount of volume sitting above what you might call its shadow. Right? And for any little piece of area down here in this shadow, any little chunk of area, I can talk about how much of volume there is directly above that chunk of area, right? And if I say, I've got a little piece of area, corresponding piece of volume, the grand total volume is going to be the sum of the volumes of these little French fries, right? The sum, all those French fries together form the total volume. So, grand total volume, sum of the French fries. How we doing? Furthermore, what is that volume? Well, the volume is the area of the base down there, dA, times this height. That height there is the difference of the z-coordinates. Right? There's a z-coordinate at the top, if you will. There's a z-coordinate at the bottom. And the height is the higher height minus the lower height. And so, let's see here. So volume is height times the area of the base let's do it like this. Little piece of volume, height times the area of the base, and boom, there's your double integral. Okay, so that's Riemann sum stuff. The subject of the domain didn't really come up very much in that discussion, other than to say that, well, look, I have to do this for, well, every piece of the domain, and so we've got, kind of all of this down here, whatever the shadow is, that's the domain that I'm going to have to use for this double integral. And now we got to figure out what that domain is. How are we doing? Everybody with me? Okay. I'm going to start by showing you what not to do. What I'm about to show you used to be a very common thing in my classes. The bigger of a deal I make out of it, then the less common it becomes, so that's good. Here's the idea. A lot of students would look at these, would look at this situation and say, okay, well, I'm looking for this curve. That curve corresponds to this curve. That curve is where the green surface and the blue surface, blue surface, intersect. All of that is valid. All that's completely correct. Now, how, though, am I going to get my hands on the idea of where these two surfaces intersect? And a lot of students mistakenly think, okay, well, each one of those surfaces is an equation, and if I want to find the points where both equations are satisfied, I'll set these equations equal to each other. That's a non sequitur. It's really not an algebraic thing, setting equations equal to each other. And I get the motivation, right? The motivation is, well, I want both equations to work, so shouldn't, it seems like you want to set them equal to each other. So, quick aside, let's talk about why this doesn't make any sense. Analogous question. If 3 is equal to 3 and 7 is equal to 7, can I ensure that both are true by setting 3 equal to 7? No. Silly nonsense. It's got nothing to do with reality. Everybody see that? So this whole thing of setting equations equal to each other that's not an algebraic. It doesn't make any algebraic sense. Okay. So is everybody comfortable with why this is wrong? Yes. Question.
But if you solve for a z,
yes, yeah, totally, yes. That's you're on the right. That's exactly the right thing to do. Let me get to that though in a minute. After I want to make sure everyone's okay with what not to do first. Okay, so you were exactly right. Let me motivate it by a geometric point of view. What we really want is to recognize that for every point x comma y. Right, wherever you might happen to be down in here in your domain, note that there is a distance up to the paraboloid and there is a distance up to the plane. Right, these are these z's that we've already talked about, these z's whose difference gives me the height of the French fry I'm actually interested in, right? So the argument should be that if I want to know where the border, where the boundary of the domain is, that boundary should be where those two heights are equal. The height up to the plane and the height up to the paraboloid should be the same because we're looking for where the plane and the paraboloid intersect. Does that make sense? Everybody good so far? So I don't want the equations to equal. I want these two different z's to equal. I want that to equal to that. And it, not exactly the same as setting the equations equal, but it's kind of got a similar sort of a feel to it. And you can see here, that's the z from the first equation, and if you were to solve, then this is the z in the second equation, and see that I am indeed setting those z's equal to each other down here. Everybody's happy? Okay, so very important little reality. Notice that this algebraic assertion that I'm making is motivated by geometry. It's motivated by a picture. Right? This is why we're doing that. Okay. And it's all downhill from here. I do want to remind y'all that there's a particular little move that from what they used to call Algebra 2 when I was in high school forever ago. I don't know what they call it now. Anyway, this particular move is called completing the square. And when I was in high school, the buzz amongst my classmates was that you don't need to know how to do completing the square because the quadratic equation does that for you in some sense. And well, that's not true. If what you're trying to do is solve a quadratic equation, then yes, but there's many other things, such as this, for example, where you need to complete the square for other reasons. So if you might be a little bit shaky, a little bit rusty on completing the square, make sure that you're good with that. Come to office hours. I'll be happy to show you how to think about that. And then notice the equation happily turns into the equation of a circle. And we've got our domain. Okay. How we doing? All right. Okay, moving along. I've said this already before, and there's going to be another couple of examples of this. The book's made some weird decisions about how to break up their book sections. And we've seen some sections previously that were really long. It contained a tremendous amount of material. How could they? Oh my God, it's so much material in one section. And then now, here we are in section 5.3, and there's really kind of one idea in section 5.3. We're going to cover this in about 5 minutes. It's just not that much to it. Anyway, like I say, there's a lot of dramatic differences in section sizes here. So, so here's the idea. Suppose you have been given an iterated integral to compute. Notice this iterated integral, if you were to go straight at it, you look at that inside integral, I have to take an antiderivative of e to the x squared, and y'all may recall, conceivably, from your single variable calculus classes, there is no closed form antiderivative of e to the x squared. And so you're dead in the water before you even get started trying to compute this iterated integral. Yeah. Okay, well, so what are we going to do? Here's the big idea. The big idea is take your iterated integral you were given, reverse engineer what is the double integral that it represents, and then slice that double integral in the other order. Right? It's something to try. It turns a question that we see here that we don't know how to solve into a different question. Who knows? Maybe we'll be able to solve the different question. And anyway, let's proceed. Okay, looking at this integral, we see y goes from 0 to 1. That means that my domain is between y equals 0 and y equals 1. Everybody good? Alrighty. Let's see, I guess I can, I'm going to go ahead and zoom out one notch here. Let's look at the inner lower bound is x equals y, and x equals y is that line. The inner upper bound is x equals 1. That's that line right there, x equals 1. So we've got a story here, right? We're looking between y equals 0 and y equals 1, and for those values of y, x goes from the blue curve to the dark blue curve, and altogether then our domain is this triangle in between those lines. Everybody see what happened there? I mean, I'm taking the bounds of the given iterated integral and just kind of working backwards to see what the actual domain is for the double integral. Once you have the domain for the double integral, then just you can slice it however you want. If I can get that to erase. Yeah, we're going to slice it however we want. I'm going to slice this now in the other order. I'm going to slice first x. Right, x goes from 0 to 1, and then for any given value of x, if I fix an x slice, right, then y starts there at y equals 0, and y ends there on that line where y equals x. And so now I've got a new question. Now, is this a win? Did we just? I mean, all we've done so far is we've taken an iterated integral, and by way of turning it back into a double integral, I've turned it now into a different iterated integral. And there is a temptation to say, well, this is just as hard as the original. Look, there's that same e to the x squared in there. Same undesirable integrand, and isn't this just as bad of a problem? And it's not, because this time my inside integral is a dy integral. The y antiderivative of e to the x squared is no problem because, x is constant. All right, so that inside integral, easy to do. You plug in your bounds, and that inside integral, aka our outside integrand, turns into x e to the x squared. Now you say, okay, well, yeah, but we've still got that e to the x squared, and now we've got to do the dx integral. Have we not only just postponed the pain, right? Well, actually, no, because now we do have an extra factor here. And again, it's just happened. We changed the order of integration. The algebra cookie crumbled a little bit differently, and now we have an easy substitution that we can make, and everything works out just fine. What do you think? Everybody okay with that? All right, so that's section 5.3. It's, like I say, it's the one idea there. Okay. All right, 5.4. So, triple integrals, a lot like double integrals. Let me just remind you, what was the big idea with double integrals? The big idea with double integrals is that we're going to rip off single variable integrals, in the sense that, all of these kinds of integrals that we've talked about so far, you've got some sort of a domain, be it one-dimensional or two-dimensional. You can chop it up into little pieces, such that on each little piece, the problem becomes simpler. On each little piece, like mass per unit area times area. Boom, no problem, right? On little pieces, you can assume that integrand is locally constant. Everything just works out fine. Okay, so chop up your domain into little pieces, multiply by an integrand appropriate to your application, add them up. So chop it up, add it up. All right. Sometimes mass is distributed over a three-dimensional region instead of a two-dimensional region, right? If you want to compute what the total amount of mass is when the mass is distributed over 3 dimensions, well, double integral is not going to cut it. Single variable integral is not going to cut it. Take this picture here, for example. If this is a box inside of which you have, let's see, what did I, suppose you have mine trimmings, right? You got a mine that's mining iron or something. Maybe in the bottom of the box, when your trimmings fall in, maybe there's a lot of iron down there. Maybe more so over on the left side because of the way the iron shoots in. I don't know. And then over, as you add more and more trimmings, well, you're digging farther and farther into the mountain. It's less iron, maybe, and so it's more so just dirt. And then maybe as you get approach, toward the top, well, that up near the top, it's not been compressed down as much, and so it's kind of fluffier dirt, and so even lower density at the top. And again, maybe even lower over in this corner because the chute doesn't shoot that far, or something like that, right? So you have wildly varying density all over this entire solid. You can't just look at the shadow and turn this into a double integral. Here's the shadow. If you were to look at little pieces of area in that shadow and ask, okay, well, sitting above that little piece, how much mass is in this slice of that solid sitting directly above this piece of the shadow, right? How much mass is in there? Hard problem. I don't know how to answer that question. The density's lower up here. The density's higher down here. I can't just multiply volume times mass per unit volume because the mass per unit volume is not constant. Not even close to constant. So this doesn't work. I cannot just slice up the shadow. Right? What I can do is take a completely different kind of a strategy, and that is to actually dice up the solid itself into a bunch of little pieces like this that are small in all three directions, and then say, okay, well, on this little piece here, there's a certain amount of mass in this little piece that has a volume. I could multiply the mass per unit volume on this piece, which is close to constant, right? Small little piece. Mass per unit volume multiply times that volume. I get little pieces of mass, and I can just add up all the pieces of mass throughout the entire solid. That's the strategy. And the way we write that down is like this. We're going to take little pieces of volume. Here's what volume looks like. Height times width times length. It's volume. I'm going to multiply volume times, in this application, mass per unit volume. Right? Mass per unit volume times volume gives me whatever it is the quantity I'm trying to add up here is mass in this case. So in purple here I have mass per unit volume times volume. It gives me mass. And I'm then going to just add up over the entire solid all of those little pieces of mass. And this is a different kind of a Riemann sum. This is not a double integral. We're multiplying by volume, not area. We're adding up in three different directions because I've got to add up, all the way across for all values of x, all the way over for all values of y, and all the way up for all values of z. You might say I've got in cubed different little sub boxes instead of in squared. So not a double integral, but morally, same basic idea. We call this a Riemann sum, right? We use the terminology triple integral as a shorthand to represent it. Here's the notation. I think of the notation, again, pretty plausible. This represents a little piece of volume, so dV for volume, right? We're adding up over three indices, so we're going to use three kind of, if you will, integral symbols to form this triple integral symbol. And again, just a shorthand notation. This is shorthand notation to represent that computational strategy. What do you think? Everybody okay? Much more to say, by the way, about how do I actually compute these, and what if the domain's not a rectangle? You have a lot to talk about, right? But just big picture structurally strategy. Chop it up, add it up over a solid. Why don't I do this? Chop it up, add it up over a solid. Algebraically looks like this. Everybody all right? Feel free if you have a question. This is, significant idea there. Okay. As with double integrals, the book spends a bunch of time talking about really cool and interesting stuff that I wish we had. I wish this was Math 431, but oh well. So for Math 219, you don't need to worry about irregular partitions. You don't need to worry about test points. Very important, very useful ideas in a math majory kind of level analysis class, which this is not. Okay. All right. Okay, so we've already kind of talked through this example. This was what you might call our motivating example. If you want to compute the mass in a solid rectangular box, the total mass is the sum of all the little pieces of mass. When you break that solid up into a bunch of tiny little pieces, the total mass is the sum of the pieces of mass. I have to write this as a triple integral symbol because I have a three-dimensional domain, not two-dimensional. And on each little piece, mass is mass per unit volume times volume. So now you'll notice here I'm using integral shorthand, right? This is really, honestly, technically a Riemann sum, and I'm not writing it using the clunky Riemann sum notation. Very streamlined and convenient to write it like this instead. But if you write it in the clunky notation, you get the Riemann sum that, well, represents exactly this triple integral. Sorry, phone off. Okay. All right. Okay. Now, one thing you might be wondering, how come with single variable integrals, we start off talking about how much area there is under a graph, and then with double integrals, we start off by talking about how much volume there is under a graph. In both cases, geometric application that comes from looking at the graph of a function. Why didn't I start that way for triple integrals? And the answer is that I can't. So just to set up the context, everybody's first picture of a single variable integral, area under a graph. And then, quick side note, yes, among other things, you can also compute a mass of a one-dimensional rod, I suppose, right? But this is always a highly secondary example. And then, let's see, for double integrals, again, we started off by looking at the graph. We looked at double integrals as computing volume under this graph surface. And then, okay, fine, we also did use double integrals to compute two-dimensional mass. So, how come I didn't continue with the green here? Well, we run out of dimensions is the problem, right? If you want to continue this pattern here, where we have a two-dimensional picture to represent a single variable integral, we have a three-dimensional picture to represent a double integral, well, we would need a four-dimensional picture to represent a triple integral, and we can't. Our brains don't work that way, right? We can't visualize four dimensions. So, crash and burn. Everybody with me? So I was kind of painted into a corner, right? We've got to figure out how we're going to represent. We've got this sort of like, well, there's a single variable integral, there's a double integral. How am I going to make sense out of triple integral? This approach doesn't make any sense. But we can, no problem, think about single variable integrals as one-dimensional distributions of mass, double integrals as two-dimensional distributions of mass, and then triple integrals, no problem. Three-dimensional distribution of mass. It's the exact same idea. Chop it up, add it up, appropriate to the dimension of the question at hand. No problem at all. Everybody see that? Okay. So, this is, I like to say, yet another reason to try to de-emphasize how much you think about these kinds of things from a graph point of view. I've already complained that, again, if you insist on thinking about integrals as being area under a graph, volume under a graph, etc., then you have a very hard time being able to relate applications like I want to compute the total quantity of some substance distributed over some region. Because what would that quantity have to do with area? What would it have to do with volume? It's really not clear. You really need to think of them in terms of Riemann sum, right? So that's point number one against graphs. Here's point number two against graphs. It's dimensionally awkward in the sense that it creates this situation of I just don't have enough dimensions. And that's a big problem. Okay. All right. Do beware that easy mistake to make, easy corner to paint yourself into is to stick to thinking about single variable integrals as areas, double integrals as volumes, and then for lack of better options, think about triple integrals in terms of volumes also. Right, and you can see the problem here. Now you have two three-dimensional pictures, but one's a double integral, one's a triple integral. Why? It seems very contradictory and confusing. Well, of course it does. You're mixing your metaphors, right? And mixing the metaphors, mixing the intuitions is bad. So there's a strong argument for thinking of integrals, primarily from the mass metaphor point of view. And, I suppose in certain instances when you're not going to get in trouble over it, I suppose you can think about, area and volume under graphs to a limited extent. Okay. All right. Pausing again. Is everybody happy with all of this? Okay. All right. So, yeah. When we were talking about double integrals, I made a case that double integrals compute volume under a graph. That's one of the really nice things about graphs. Again, I'll give it that. But we can use a double integral to compute a volume under a graph where we had previously used iterated integrals to compute volumes under the graph, and our punchline was that double integrals and iterated integrals are equal, and that was awesome and allowed us to compute all sorts of things. Well, I can't do that either, right? That picture again would be here. And I don't have that, so I can't make that argument. So what I'm going to have to do is just assert that there is a very rigorous, in fact, quite a bit more rigorous than the volume point of view I gave you with double integrals, perfectly rigorous argument that shows that triple integrals can be computed with iterated integrals. Just following that pattern, it's exactly what you would think, and that works just fine. So again, I can't show you a geometric argument because we don't have a four-dimensional. We can't visualize in 4 dimensions. But same punchline, and I hope that's believable and hopefully also satisfying. Okay. Notice, by the way, that your domain, right? The range of values of x are your x bounds. The range of values of y is your y bounds, and your range of values of z are your z bounds. And it doesn't even matter. Maybe you do your z bounds first. Fine, no problem. Maybe you do your y bounds second on the inside, and then let's see here, your x bounds last inside. Got to be careful with that terminology. Either way, as long as they pair up, right? So any shuffling of the 3 things, I can only do so many things with my fingers, but as long as they pair up, that's fine. Any of the 6 different orderings is all good. Okay. All right. Okay, so here's our strategic diagram. There's lots of applications that I can represent with Riemann sums. It's our first observation. Lots of applications I can represent with Riemann sums. I can't think about this stuff from the graph point of view. There is no argument, because not only is there no good argument connecting, mass to a 4-dimensional whatever that would be, but furthermore, we don't even know what a 4-dimensional such thing is anyway, right? So don't make that mistake. There is no volume or whatever that thing is that we can argue about. Likewise, this argument doesn't make sense either. You can't compute mass and argue that I can immediately write down an iterated integral with mass per unit volume times length. It's a mismatch. There's no case to be made there, so that doesn't work either. So the big benefit then of my assertion that triple integrals can be computed with iterated integrals is it allows us to connect the thing that relates to applications to the thing that I can compute with the fundamental theorem. So we have the same sort of 3-step process, right? If you want to compute a, whatever your application might be, population or mass or work or whatever, 3-step process just like with double integrals, just triple integrals instead. Everybody see the sort of the flow, why we need all three steps? Okay. All right. So let's see an example. So we're going to compute a mass. We've already talked about how to write masses as triple integrals. So I'm going to say phase one, step one in the compute the mass question is already established. Mass is a triple integral. We argued above that triple integrals are iterated integrals. Notice the bounds, right? So my x bounds are the bounds for my x integral. Doesn't matter where it is in the three sort of steps. Let's see here. The y bounds are the bounds on the y integral. And the z, let's see here. Oh, colors. Red. The z range, 0 to 1, are the bounds for our z integral. So, step 1, application is a triple integral. Step 2, triple integral is an iterated integral. Step 3, punch it up, and there's some algebra to be done here. But it's all fundamental theorem of calculus, antiderivatives, plug in, etc. And do be careful. Got to think through all the details with that. So, for example, on this inside integral here, when you're looking at that, the first integral that you compute, the inside integral, remember z is your variable. X and y, further to the outside, those are to be understood to be constants for the purposes of that inside integral. So this x and y, constants, as is that 2, by the way. Right? But let me just focus on the x and the y. The x and y being constants, they just come along for the ride in that term, and you don't right? You don't turn this x into 1/2 x squared, because x is a constant, not a variable. And then from a what do you got left standpoint, well, the antiderivative of 2z is z squared. Everybody good with that? Notice the familiarity, right? It's the same move that we would do with double integrals. It's just, 3 of them instead of 2 of them. Again, also, my little personal preference is to take these bounds and don't just copy the bounds. Also recognize in there what it is that's equal to those values. And so say z equals 0 to z equals 1 so that you won't accidentally plug in for the wrong thing. And again, that can mess you up too. Everybody happy? Everybody's so quiet. Is it all just making great sense, I hope? Okay. All right. Okay, so here's where things get a little weird. Non-rectangular domains. Now, we saw how this worked for double integrals. And if you think back to the argument that I made for double integrals, it involved drawing a graph picture, right? And I had to draw the graph picture, and then the punchline of the argument was that the domain's all that matters. The integrand, why are we drawing a vertical, why are we drawing the integrand as a vertical axis when it's got nothing to do with the bounds? The bounds are only about the domain. So the same thing is true here, but I can't draw that picture because, again, it's a 4-dimensional picture. But what I can do is assert and hope that you're willing to believe that, again, it's all about just the domain, and it's all about the same process of slice orthogonal to a coordinate axis. Here we're going to slice perpendicular to the x-axis first, no particular reason. You look at what those slices look like. You think about various of those slices at various different values of that variable x. You notice where's the first one, where's the last one. The bounds come from looking at where those first and last slices are. Right? Then you fix a value of that variable, thus fixing our attention on a single slice, and then repeat. Right? We go back up to the beginning in some sense. So we've got our X process done, and now go on to the next variable. So now we're going to slice, let's say, orthogonal to the, let's say, the Y axis. And you got to, think geometrically here now. What happens if I take this X slice, and our X slice is sitting here like this, right? It's a flat vertical thing, and if I slice perpendicular to the y-axis, what happens when I take this slice and I slice the slice, right? And I'm going to get, I claim, when I take a y slice, I get a little line segment there. Everybody see that geometrically? And again, you got to think about first and last. And so let's see here. It starts there, which gives me my first value of y, and then it's going to end there, which gives me my last value of y. So it's just like with double integrals. Big difference being that we then have to go through and do a third step, which is, so again, back up to the beginning again. And now we're going to slice orthogonal to the last coordinate axis. Our slice of our slice was this. That's our y slice of our x slice. And let's see here. We're going to need to know, where does it start? Where does it end? Well, z starts at that point. That's the lower bound. Z ends at that point. That gives me my upper bound. And you see here, there they are. And so, three-step process instead of two. You do your X slicing to get these two-dimensional slices. Y slicing gives you one-dimensional slices of slices. And then the Z slicing dices that up completely and gives you your Z bounds. That's all very generic and general. This is a non-specific domain. We're going to talk through next time the details of how does this actually break down for various different solid shapes. And I've got some cool tricks to show you on how to streamline that process for various different shapes. Y'all have a good one. See you later.